We were talking about things like if we increase the flow velocity, then the heat transfer increases. And I also said that that is good, but at the same time, if we increase velocity, then the frictional pressure drop will also increase. Right? So there's a balance between the two. Plus, there are other considerations I mentioned. One is erosion. Like if you have flow with a high velocity, it might erode the surface. Plus, there can be also vibration of the structure. Right? So these were all mentioned yesterday. Now, if the velocity is too low, then there may be more fouling, because then there is greater residence time, greater time that the fluid spends within the heat exchanger, because it's flowing at a smaller rate, right? And that leads to more fouling. Deposits will form more readily if the flow velocity is low. Now, we have to obviously have some balance amongst these things, and that gives us this kind of range of velocities. Okay. This table is again taken from Lee's book, and it says that let's see, if you have water, it's 1.4 to 2.8 meter per second. It says this is an economic velocity range. So like too high means too pumping power, but it takes into consideration other factors also, as I said, fouling, then erosion, then vibration issues. So it's kind of like a range over which you should try to restrict yourself, but sometimes you might have to go a little bit here and there. Uh, but these are recommended ranges. Now let's go to shell and tube heat exchangers. So very quickly,
Shell and tube heat exchangers will look something like this. With this design, you normally find the inlet and the outlet for one fluid at the very end of the heat exchanger, known as the header. Then we have another inlet and outlet for fluid 2 on the main body, known as the shell.
what he mentioned is that in this design, but doesn't mean that all shell and tube heat exchangers have got exactly this design. There can be variations in the number of shell passes as well as the number of tube passes. Okay, so even your undergraduate textbook, I think, has various figures, schematic figures of different designs of shell and tube heat exchanger. But this video is still good because it shows you three-dimensional views as much as possible here.
Inside the unit, we have the tubes. These bend and loop around to start and finish at the tube plate, which sits between the shell and the header. The tubes will usually also pass through some baffles, which are sheets of metal. We will see how these work in just a moment. The header, as well as the tubes, can be removed for cleaning, repairs, and maintenance. Inside the header is a sheet of metal known as the divider, or the partition. This separates the tube ends, enabling the fluid to flow into and out of the tubes. Fluid 1 will flow through the header, into and around the tubes, then back to the header. the shell and surround the outside of the tubes. The baffles will partially block the flow, which will force the fluid to turn multiple times. This creates a turbulent flow and ensures that fluid 2 mixes with itself, which ensures maximum heat transfer. For example, we might find this in a pharmaceutical factory with a boiler providing steam into the shell, which surrounds the tubes. A chemical product is then pumped through the tubes, and this absorbs the heat of the steam through the tube wall. So this product is going to exit the heat exchanger much warmer. Meanwhile, the steam will start to condense into a liquid and flow back to the boiler to pick up more heat and repeat the cycle. Additionally, these are used in refrigeration applications, like this industrial chiller. We have the water flowing through the tubes and the hot refrigerant in the shell. The water will absorb the heat of the refrigerant so that it can transport this to the cooling tower where it will be injected into the atmosphere. The water returns cooler to pick up more unwanted thermal energy from the chiller. We have covered how chillers work in great detail previously. Do check those out. I'll leave a link for you in the video description down below. Double pipe or tube-in-tube type heat exchangers will look something like this. This is similar to the shell and tube heat exchanger because essentially we just have a tube which runs back and forth several times between an inlet and an outlet. This is surrounded by a shell which has another inlet and outlet. The metal frame will hold the unit in place. Typically, these will all be made from stainless steel. One fluid will flow through the tube and another will flow through the shell. The two fluids are separated by the tube wall and transfer thermal energy through this tube wall. The different configurations result in different temperature profiles and heat transfer. In this design, the bend at each end isn't utilized for heat transfer, and heat can be wasted here. However, manufacturing this heat exchanger is cheaper and obviously easier. Other designs like this chamber, which are often found in oil refineries, will encapsulate the bend but utilize the surface area for heat transfer. This version normally uses multiple tubes to maximize the surface area and thus increase the heat transfer, although this will also increase the resistance. These are a fairly simple heat exchanger design and are very common, particularly in food processing as well as pharmaceutical production. For example, we might have a dairy product flowing through the tube, and then we have hot water or maybe steam flowing in the opposite direction through the shell, which will warm the product up to a certain temperature before it is mixed with some other ingredients and then bottled. Check out one of these videos to continue learning about mechanical and thermal engineering, as this is the end of the video. Don't forget.
Okay, and there's another video, but this is more than 7 minutes, so I'll not be playing this fully. I'll give you the link. So this is by some company, HRS Heat Exchangers, and this shows the constructional details as an entire manufacturing process. So the title of the video says time-lapse manufacturing of large shell and tube heat exchangers. Okay, so if you watch this fully, then you will know the sequence in which these things are put together, manufactured and assembled. Not really the main focus of our course, because we are just doing the design, but it's good to know. So I'll just randomly pick up somewhere.
The baffle cage is placed in the shell.
This also gives you some idea over the size of the heat exchanger, because you will see human beings there. So you can easily compare the sizes. See, these are so big. Not all of these are big, but this particular video is on large shell and tube heat exchangers.
The first tubes are inserted one by one. Only the first tube plate is welded at this time. finishing of the second tube plate.
Okay, so tubes have been inserted, and then you see this flange here.
The remaining tubes are inserted. When all the tubes are inserted, they're point welded to the tube plate. Now the orbital welding rotor expansion work can begin. Two operators begin the orbital welding. Tubes are welded in a zigzag pattern to avoid tension on the tube plate. The tubes are expanded, assuring a perfect fit. The unit has been pressure tested and is prepared for transportation.
So he said the unit has been pressure tested and is now ready for transportation. So these are pressure tested because this is the kind of a vessel which has to withstand some pressure. I don't know what is the value for this one, but these are typically pressure tested also. Okay, so I'll stop here with these videos, and let's go back to the PPT that we were looking at. We're talking about these velocities, reasonable velocities. Then this is a construction, and you already know this, and this is a shell sheet, and these are baffles. I think I'm not sure, but in the manufacturing video, you'll probably see baffles also. I don't remember fully. And these baffles look like this. So if you take a full circular plate, out of that, some 25 to 30% is cut off. Okay, in this case, so if you say this one, then it goes like this. So the lower part is cut off. And in this case, it looks like this. So the upper part has been cut off. Okay, so what's the purpose of the baffles? Why do we need baffles? Baffles have a secondary function. They help hold the tubes, right, in place. But that's not the primary function. What is the primary function? Yeah, so it increases the length of the fluid flow, and it also, so that heat transfer becomes better, and it creates turbulence also, right? If the fluid passed straight through, then that wouldn't have been good. So you're forcing the fluid to go like this and creating obstructions in the path of the fluid. So that creates more turbulence. And I think you know that if you have turbulence, then the heat transfer, all mixing processes, all transport processes actually improve if you go from laminar to turbulent, right? Now, another important point is that heat exchangers are often designed using some codes. Okay, code doesn't mean your computer codes. Okay, these are codes for which give you the various steps and various practices in designing a heat exchanger. So this is a tubular exchanger manufacturers association, TEMA. So I worked in industry before joining IIT for a very short duration, but during that period of time, I'd use this TEMA code to design heat exchangers. Okay, and this is, if you go to tema.org, you will get design codes and standards. for heat exchangers. You don't have to do it. I'm just mentioning that when you work as a professional engineer, this might be required. And nowadays, these TEMA codes are actually implemented in actual softwares where all the processes are inbuilt. So you can run the software code to basically design your heat exchanger. But that has got all the equations, all practices built into it. TEMA is not the only one. There are other codes also. Okay, so shell and tube heat exchangers provide a surface area density. We used a notation for this that we called it a beta, right? Beta is the area divided by the volume. So that ranges from 50 to 500 meters square per meter cubed. And these are easily cleaned. So you can, I think there is some mention of cleaning in that time lapse video also. Right. So this is one shell pass. Okay. So this is going like this, just goes out, and this is through the tubes. Now here you have flow going like this through the tubes, going back like this, okay, and through the shell it goes like this. So there are various other configurations also. This is something about the nomenclatures. Number one is shell, number two are tube sheets. Okay, we saw the tube sheets in that video properly. Three is these are channels. Four is channel cover. Channel because this is like inflow outflow channels basically. And five are baffles. Okay. Six are some separators, I think, but he has not mentioned six here. Right. So these are just some names, but we also need to be able to go to some calculations. So for that, we need some nomenclatures. The nomenclatures are, this is tube length, this B is baffle spacing. Between two baffles, there is some spacing. Number of tubes, number of passes, shell inside diameter. DS is shell inside diameter. And NB, number of baffles. So the baffle spacing is LT divided by NB plus 1, as you can make out from here, from the figure. Okay, so the shell and tube, in a shell and tube heat exchanger, you see that what you learned in undergraduate heat transfer, this is all relevant because you have internal flow, that is flow through the tubes, that's internal flow, which you studied. You studied this parabolic velocity profile, laminar flow, turbulent flow, uh, entrance length, fully developed flow, all sorts of things which you studied, those are applicable there. Now you also studied external flow, but the external flow you studied in undergraduate is like flow over a flat plate or flow past a cylinder. This is much more complicated external flow because it's going like this in the shell, and also it's going to be turbulent, necessarily turbulent. All right. So what do we want to be able to calculate? So ultimately, what is the objective? Ultimately, we should be, when we design, we should be able to say something about the area that is required for heat transfer. There's certain amount of heat that you want to transfer. So you want to take water, let's say from 10 degrees Celsius to 80 degrees Celsius. Water is coming at a certain flow rate. The water inlet temperature. So that this much heat needs to be transferred. Okay, you can do m dot Cp delta T, that sort of thing, and calculate this much amount of heat which is required to be transferred. But then to transfer that heat, you need some area, right? And that area needs to be distributed amongst various tubes. Correct? The heat transfer is taking place through the tube surfaces. So that area calculation we have to be able to do. And that area calculation will also depend on overall heat transfer coefficient U, right? Because the heat transfer is proportional to overall heat transfer coefficient. It's also proportional to the area and some effective temperature difference, right? We wrote in yesterday's class Q equal to UA, then some factor, then delta TLM, correct? So these things are all coming into picture. So our purpose is that, okay, we want to get some estimate of that area and then distribute that area in these many tubes. And so many tubes of this some diameter, some chosen diameter, they have to be accommodated in a shell. So the shell size also will come from all these calculations. So that's the purpose. Now you see that everything is linked, and heat transfer is obviously related to that U, overall heat transfer coefficient. Now the overall heat transfer coefficient depends on HI as well as HO. HI is the heat transfer coefficient for flow inside the tube, and HO is the heat transfer coefficient outside the tubes, right? So all these things you have to be able to calculate. So to calculate heat transfer coefficient, you need things like velocities, and you need to be able to calculate Reynolds number, so you know whether it's laminar flow or turbulent flow. Then you have to make a judgment as to whether it can be entry length flow or fully developed flow. Okay, you need all these things because then you will be able to identify some correlations which are applicable. Okay, ultimately in heat transfer, whatever you learned in undergraduate, like it comes down to some correlations, right? Finally, and then you get HI, then you get HO. Using these, you get that overall heat transfer coefficient, and then you have to be able to say something about LMTD. Then you get that area and all that for a known heat, for a desirable, for a heat transfer, total heat transfer that you are desiring, right? So let's see how to proceed. So first, let's look at the tube layout, because this is in your hands. This I mentioned some time back that, okay, you can have this sort of flow pattern. So this is square pitch, but you can also have a triangular pitch. So in this case, you can have more turbulence generated in the flow, right? Because this flow, it encounters another tube in its path, whereas this flow can kind of bypass the tubes to some extent, right? But here it hits another tube, then it will pass the tubes, so there will be heat transfer. Then after coming here, maybe a little bit of bypass, but this flow again encounters another tube. So that sort of thing. And there's some rule that the tube pitch should not exceed 1.25 times the outside diameter of the tubes. So what is pitch? Pitch will be between this and this, correct? Or between this and this in the triangular arrangement. So the tube arrangement will generate different kinds of different values of heat transfer. Because the flow changes, if the flow changes, the heat transfer coefficient will also change. Now, we will expect that in the second case, in the triangular pitch case, since you are generating more turbulence, you will be able to get better heat transfer, right? Now, these are some of the arrangements. So this is triangular, 30-degree, rotated triangular and all that. This becomes square, and this is rotated square. So these are some of the arrangements. So if you have the same tube pitch and same flow rate, then the tube layouts in decreasing order of shell side heat transfer coefficient. We are talking about the shell side heat transfer coefficient. Decreasing order of shell side heat transfer coefficient are 30 degree, 45 degree, 60 degree and 90 degree. So this will give you the highest heat transfer coefficient. If you go to 90 degree, which is this one, then you will get the lowest heat transfer coefficient because of bypass kind of thing, not disturbing the flow enough and all that. Okay, so the 90 degree layout has the lowest heat transfer coefficient and it also has the lowest pressure drop, as you would expect, because you're not obstructing the flow much. Right. Then let's see some calculations. So for these arrangements, you can calculate an equivalent diameter. So this is a square pitch layout, this is a triangular pitch layout. And we define an equivalent diameter, which is 4a by p. So what are 4a by p? Now, for the square pitch layout, this is what we are getting. Now, can you take a look at this one and tell me whether it seems reasonable or not? Is okay? So what is PT square? PT square is PT is the tube pitch. So PT square is this whole area, right? But you don't have the whole area because this much, like this, like these two, bottom, these two, they need to be subtracted. Okay, this is what we have done here. So essentially it's 4 times PT squared minus 1/4 of tube outside area. I mean cross section area, but based on the outside diameter. Right. So this is pi do. Do is the outside diameter. What is pi do physically? It's the definition here says heated perimeter. P heated is heated perimeter. So why is it pi do? Because this much, this much, this much, this much, they're all getting heated. Okay. Heated meaning there is heat transfer taking place through those perimeters, right? So all 4 added up will give you pi do. Now you can do a similar sort of thing for the triangular pitch layout, and that's shown here. That we are not going to derive in class, that you can do at home. You can check this out, but similar principle. Now apart from what we have already seen, all dimensions, see, this has got a di, this has also got a do. Now there is also a cross flow area of the shell, which is defined like this. Okay, so this requires a little bit of discussion. So this is a cross flow area, maybe I'll write it here. So what's this? CT, just remember what is CT. CT for the square layout is just PT minus DO, right? PT minus DO. But what's this? Now there's a little bit of problem with the notations here. Again, I think this is, I know it's a problem, but I've still copied it from the book to make you aware that the book has some of these problems. So this is AC. This is also AC. But what is this AC? This is this area, which is essentially the shaded area, correct? So in a tube arrangement, so this is a particular unit layout, you can say, you this thing, that square that you see, if you multiply it, okay, if you have large number of them, then you get the complete tube layout, right? The shell and tube heat exchanger will obviously not have just this one, it will have few more, many more. And that area AC is actually this shaded area. But here we are talking about some other area, but he still calls it AC in the book. But this is a cross flow area. Maybe you can write it like ACR. Now, what is that cross flow area? So you have these tubes. So if these are the tubes, then the area that we were talking about is, as the flow goes through this, it sees this area, right? This cross sectional area here. But there is also another area which goes like this, because the shell fluid will flow like this, right? Sometimes. And for that, we need DSCTB. Now keep these figures in your mind and go to this figure and then try to interpret this particular area. So this is ds, right? This is b. There is a ct also. So what is ct? Ct is this one, or maybe you can say this one, same thing, right? This is ct. So what is ct into b? So we have these. This is ct. This is also ct. And there is a dimension perpendicular to this, okay, between baffles. We call that, what do we call that? Between baffles? B, right? So if this is B, then this is CT into B, correct? You're looking from the top, you will see CT into B. All right. So this interpretation we can understand. What about ds divided by pt? This is ds. So this is the number of such units basically. So ds over pt. Isn't it? Pt is between two tubes, and ds is the whole dimension. So if you do ds by pt, you get multiple, actually the numbers that you get in this direction. You will understand what I'm saying if you're able to visualize this, otherwise you will not be able to follow. Okay, so imagine the tube bundle situation in your mind. That's why I showed the video at the beginning of the class. The 3D thing you have to keep in mind. These things are obviously 3D, not how they look like on the screen. Okay, so I think that should be all right. And there are a few other quantities also. So for example, there is a dr, which is do divided by dt. And ct is pt minus do. No, 1 minute. There is no dt. There should be di. There should be di. Now there is a tube pitch ratio also, which is defined as PR, PT over DO. And CT we have also seen. CT is PT minus DO. So CT is called tube clearance. Now we are doing all these things, but we can get the number of tubes also. For a particular shell and tube arrangement, we want to get the number of tubes. So to get the number of tubes, we use a tube count constant multiplied by this thing. So there is a pi ds squared by 4. Pi ds squared by 4 is like you take the entire shell and you take a cross section. So that's the area, shell area. And there is a shaded area which will come to in 1 minute. And CTP is a tube count constant. Okay. So the arrangement of tubes in a shell and tube heat exchanger is not exactly uniform, because there is some clearance between the shell and the outer tube circle, and there are some separators, tube pass lanes, etc., etc. So there is a little bit of adjustment. So this CTP is not actually 1. Okay, if CTP was 1, then the number of tubes would have been pi ds squared by 4 divided by this shaded area which we are coming to. So what is this shaded area? So look at this again. For a square pitch layout, the shaded area is just PT squared. So what is shaded? Actually, it's a bit confusing in the sense that this is the shaded area, but we are not calling this one the shaded area. Okay, in this figure, this is the shaded area, but the shaded area which he is referring to after that figure is some CL, which is a tube layout constant multiplied by PT square. Okay. So for square pitch layout, it's just PT square. So let's understand in a very simple way. This is pi ds squared by 4 divided by PT square. Pi ds squared by 4 is for the entire shell. This will give you pi ds squared by 4, and for a unit, like the unit that we are talking about, this sort of thing, right? Tubes are going like this. This pattern is repeated. This is the tube layout pattern. This is repeated multiple times to give you the total arrangement, right? So this area, this whole thing is PT squared, right? So if you take this pi ds squared by 4, then you divide it by this, then you get the number of tubes, but you need some arrangement also, some adjustment also. So that adjustment is the CTP thing that we are talking about. So CTP from the previous slide is the tube count constant, which is not 1, but it's kind of close to 1. This is because the arrangement cannot be made uniform, because there will be some structural component here and there which will disturb a uniform arrangement. So close to 1, but not equal to 1, less than 1. Now just think about it. Pi ds squared by 4. Okay. So pi ds squared by 4 divided by shaded area. If you don't bother about shaded area so much, just think about the square arrangement first. So then this is what is this? This is pt square, right? So this area, take this area divided by this. Why should this give the number of tubes? Or will it give 1/4 the number of tubes? Yeah, yeah. It's basically 1/4 from each corner. Okay, so you should not think that if you do this, then you get 1/4 the total number of tubes. That's not correct. Okay, that argument, hopefully you can play it in your mind and it should be all right. So this gives you a number, but it's imperfect because of some disruptions in tube arrangements here and there, constructional issue. So that's why you multiply it by that CTP. Okay, so this is CL equal to 1 for square pitch layout. So this similar sort of discussion can be done for a triangular pitch layout also, but there the tube layout constant is a sine of 60 degree. Okay, so this is again, I think you can do this at home. So I'll not spend much time on this. Obviously, this arrangement is different. So imagine this arrangement put together in a shell, right? So some dimensions will change because these things are at angles, right? And we'll think about this. You can think about this at home, or else if you still have questions, those can be discussed in tomorrow's class. Okay. So it's CTP by CL, and rest of it we have already seen. Number of, so this is important in the sense that we get, if we choose an arrangement, let's say we choose a square arrangement, then this sort of calculation gives you the number of tubes, isn't it? That's the bare minimum thing to start with, right? You choose an arrangement, let's say a triangular arrangement, a square arrangement, then this sort of calculation gives you the number of tubes. That's important. Without number of tubes, what will you do? You can't do any calculation. And maybe a little difficult to see, but these are sort of various calculations for the tube side and the shell side. But this is an equivalent. This one, can you see this one? Or too difficult to read? I think it's probably okay. Right? So I wanted to show everything on one page, so that's why this is again taken from the book only. So this one is that effective diameter, which we have already seen, and here you will see the cross flow area, and yeah, so just let's just look at this one. This is, I'm jumping a few slides. We'll come back to this in detail later on. But for the purpose of today's class, we don't have that much time. So just let's look at this one. So there's some problem with the triangular arrangement and all that, triangular pitch layout. So the number of tubes is calculated using this sort of expression that we were discussing a few minutes back. That's the number of tubes. And the number of tubes come out to be something which is rounded off to get number 138. The number of tubes actually came out to be 138.189 according to that calculation. So we just say that's 138. Where is this used? This gives you some cross flow area, which depends on the number of tubes as well as the number of passes. Number of passes I did not discuss, but you can kind of understand that okay, all right, cross flow area will be pi di squared by 4. This is for the tube side. Each tube has, so this is a tube. Tube has an internal diameter as well as an outer diameter. So this is di, right? This is di. And the area is, this area is pi di squared by 4. So we can get we can calculate a cross sectional area, cross flow area for tube flow. Then we can use that area and also use the m dot information. There will be an m dot information flow through tubes. There's an m dot information. So we can use this to get v1, that is velocity through the tubes, and we can then calculate a Reynolds number. Okay, so I jumped a few slides and to just show you that okay, you got the number of tubes, then you get this area, and use that area to get the velocity. And if you get the velocity, you get a Reynolds number. If you get the Reynolds number, then you can go to obviously the correlations that you have. So the correlations are listed in this kind of a long table. Okay, so there is a correlation for tube side laminar flow, tube side turbulent flow, stuff like that. Okay, the number of tubes, from that you get area, you have m dot, so from that you get velocity, and once you get velocity with other dimensions, you can get the Reynolds number. Once you got Reynolds number, you get Nusselt number. From Nusselt number, you get heat transfer coefficient. You do that for the shell side, you do that for the tube side, you combine them, you get u. You know, that's the way we're going to go. But of course, we cannot complete this discussion today. So we will complete this discussion on Friday. But let's see if there's anything else. Yeah, well, let's do this. Let's do this one. Just take the next couple of minutes to at least read this problem, because we will tackle this problem in Friday's class. Just read this slowly. My approach is that in Thursday's class, you do some problems, but in lecture classes also, I touch upon some problems. Okay, lecture classes, I do not do just the theory part of it. I also bring up some problems for which we can discuss some design aspects. Okay, so please read this one. Kind of an automotive application. So there is engine oil which gets heated, and then you are cooling it with an engine coolant, which has got 50% ethylene glycol. Mass flow rates are given for the engine oil as well as for ethylene glycol, and the tube material is given, fouling factors are given. Engine oil will flow through the tubes. Pressure drop for each fluid, maximum pressure drop is limited to 10 kilopascal. Okay. and the volume of the heat exchanger needs to be minimized. So this is optimization. Volume of the heat exchanger needs to be minimized. So you just don't make any heat exchanger. This heat exchanger has to obey constraints. What are the constraints? The pressure drops. Okay, and optimized in the sense that the volume should be minimized. Okay, so we'll stop here because I think the next class is waiting. Thank you.